I thank you, Randy. It's always a pleasure to be able to get online with you and your audience to talk about subjects of mutual interest. And one of the ones that I've been following for quite some time and study and trying to share knowledge across the industry is the topic of moisture in the insulation system of liquid immersed transformers. And I thought I'd start with shock value, Randy. This is a recent result of a generator, single phase generator step up transformer, a 400 kV, directed oil flow water cooled transformer, where it failed in service after being dried, so to speak, where they had processed the oil a few weeks before this event occurred. The information they had at the time said, well, it looks dry. The oil is dry, but unfortunately, the solid insulation was not in the same condition. So fortunately, in this case, this utility had a spare on site, which they avoided having to wait 2 or 3 years for a new one, and they were able to move this out and then insert it. So at the end of the presentation, I'll go into more detail about this failure and the resulting forensic analysis that Kinectrics had at the time. So, but why worry about moisture? Well, we all know by nature, so to speak, that oil and water don't mix easily. They will mix if the temperature of the oil is high enough. The oil expands and then the moisture can come out of the paper and then fill the little gaps in the space between the water molecules. But moisture affects the dielectric performance of the solid insulation. And the picture there you see with the pretty pictures of partial discharge across the surface, in this case of pressboard, wet pressboard materials. That's typically between the low and high voltage windings and at the ends of the windings are curving around the coils. This is the evidence that the pressboard is wet, and this is partial discharge that is set up. It does not get better as it ages. This it can degrade other non-cellulose insulations in transformer by means of hydrolysis. But moisture reduces the volume resistivity in the oil, and this is particularly concerning when you're looking at HVDC transformers. This is a key item of interest for those people with that, is the resistivity of the oil in the DC transformers. The other thing is that water can have an undesirable other chemical reaction inside, like rust. Yeah, everybody thinks we have water, rust, metal and rust, and it's oil. It's never going to rust. Well, it does. You have iron. You know, if you think of the equation, Fe is iron plus H2O. The O2 transfers to the Fe, that's ferrous oxide, rust, and you're left with hydrogen. So it's a chemical reaction. And that's what I tell people or ask people to consider when you next look at your favorite transformer. Think of it as a chemical reactor at work, because that's exactly what it is. You have materials, organic materials, oil and paper, and water. And the active part is the heat generated by the windings in the core. So, and this chemical reaction takes place continuously. And like any chemical reaction, the more heat or energy applied to a chemical reaction, the faster it happens, the faster it reacts and carries on. So we're looking at this, and the other thing is to be concerned about is with that picture on the lower right is the evidence of what we call bubbling, when the moisture in the paper on the conductors in the windings reaches the point of being too much, and the conductor temperature at the right spot where normally the moisture moves in and out of the paper by diffusion. It moves back and forth. It becomes so wet that the diffusion stops and you have bubbles. What you see there are water vapor bubbles or steam on top and below. So what's happened here is that you have reduced the dielectric capacity between turns of the winding, or in this case, between the sections, and the result is an immediate turn-to-turn dielectric failure. Boom, the transformer's life is over. This is what we want to avoid happening in the transformer. The other side is the oil itself. And we talk about saturation of the oil with water. And this is from some work done for EPRI by Valerie Davidoff, a researcher from Australia, showing what oil looks like when it's on the left-hand side when the relative saturation, or when you think of relative saturation of a fluid in a fluid, think of relative humidity of a fluid in the air, like water in the air. Relative humidity, that's what the weatherman talks about. He doesn't talk about relative saturation, of course. It's relative humidity. So in water in an oil, water in another fluid, that's talked about in terms of relative saturation. In the middle is a beaker of oil that has reached saturation, where the relative saturation is at or just over 100%, and it looks cloudy, foggy, just as air would be when it reaches 100% humidity in the air. It's foggy. And on the right-hand side, you'll see where the oil has now become super saturated with moisture. And in the bottom of that beaker can be found water, free water. In other words, inside that beaker, the water has condensed in the oil and fallen to the bottom, and it basically has rained inside that beaker. The same situation can happen inside the transformer. That's why we're concerned about how much water is held by the oil. So I keep telling people, think about relative saturation and related to oil temperature. There's so much in the history of looking at parts per million of water content, and let's look at how we can understand this a little better. So the laboratory, you send a sample to the laboratory, and they've measured, come back to you and says, okay, there's 50 parts per million of water in this sample. Fortunately, the fellow taking the sample at the time has recorded the temperature of the sample, 30 degrees C. You can plot it on this saturation curve, and that's what this is. It's the moisture in oil saturation curves at different levels of moisture saturation of the oil. This blue dot falls on the line of 60% saturation. This is not good. It means that it's 60%, its dielectric capacity has been reduced by more than 50%. And guarantee you that that transformer is wet. If they had taken the sample, let's assume the sample temperature was somewhere up around 65 degrees C, the laboratory has measured 50 parts per million, then the saturation of that water in oil is just under 20%. And that's the limit of saturation of moisture in the oil as defined by in the IEEE standard, IEC standards for moisture content in the oil, 20%. So it's on the border, so to speak. If the sample was at 20 degrees C, it's probably rained already inside the transformer, because at that level, 50 parts per million at 20 degrees C is the water condensation temperature. It's reached 100% saturation. People say, well, how can this be ppm? We've been talking about it for years and years and years, and that's true. The water content on paper, when the laboratory does that Carl Fisher test, it measures three things. It measures absolute water content in that oil sample. And the absolute water content of oil in the sample consists of three parts. It's the relative saturation. In other words, the moisture is dissolved in the oil. It measures bound water. So the water molecules that have attached themselves to things like acids, attach themselves to like particles that may be floating around in the oil, or cellulose fibers floating around in the oil, or free water. So it measures three things: absolute water content in the oil. The interest from a moisture point of view in transformers is the relative saturation, because the bound water doesn't move. It stays there. It's never going to move. The relative saturation interacts between the oil and the paper. Because remember, paper acts like a big sponge inside there. Oil and water don't mix. What the oil doesn't want, the paper's there to soak it up like a big sponge. But when it gets hot, it pushes the water into the oil. So when you're taking samples, find a way to take the sample temperature of the sample when you take the sample, not when the sample's back in the truck, and not when the sample's back in the shop, at the time you take the sample, and you'll be able to understand how saturated is that oil. The other thing is there's no impact on the dielectric capacity of the oil. And here we're looking at this is from a C-grade technical brochure, 741. And it's showing, in this case, new oil, the percentage of breakdown volts to D1862, 2 millimeter gap. So the left-hand side shows the breakdown volts in terms of percent. And across the bottom is the percent saturation of moisture in the oil, as measured by, in this case, a moisture sensor. And you can see if the moisture sensor is just below 20% or at 20%, then the breakdown volts is at 90% of what it would be if it was less than 20% saturated. If that oil is like 75% saturated, that oil has lost 70% of its dielectric capacity. That's the impact of water, dielectric capacity of water in the oil. It's related to moisture saturation. That's quite important. And like Chris was mentioning before, when we want to get this data and we trend the data over time, there are ways to monitor the moisture in the oil of a transformer, moisture sensors, and the temperature associated with it to be able to follow this movement in and out of the water. And why we should be concerned about it is because it's one of the bigger impacts on the aging of the solid insulation of the transformer. And so its temperature is a big contributor to aging of the paper around the conductors. Moisture certainly is. Oxygen dissolved in the oil to some degree, and time. And the effect of aging on the paper is that it reduces the mechanical strength of the insulating paper. And this effect is irreversible. Once it's aged, just like humans. Once you've reached the age, as you age, it's irreversible. Now, the other thing is dielectric strength of the paper is unaffected until the paper ruptures. What you're seeing here is a sample of a conductor taken from a rectifier transformer that failed under a small short circuit, but something it should have been able to sustain. And the company I was with at the time, we were doing sampling or testing of the oil in the lab, and we informed him that there's, this thing's generating furans like crazy. It's a high temperature. You got a high temperature problem inside this transformer somewhere. And basically they said, go away. None of my temperature alarms have gone off. So I think you're smoking grass. Well, it turns out after this failed and the forensic examinations and getting the whole story, the rectifier manufacturer, it was a rectifier transformer. The person who made the rectifier and the transformer did not communicate with each other as to what was the total expected harmonic content going to be. You can design a transformer for any amount of expected harmonic content that the load is going to have. They just need to know it. So this is the impact of harmonics overheating the conductors. It did not get reflected in the winding temperature simulator because it can't. And it was not really reflected in the oil temperature because it was of such a large volume of oil. But you can see what impact was. The short circuit and the ripping and the tearing of the paper has lost all of its mechanical strength. And you can see how the conductors have separated themselves due to the short circuit impact on that transformer. That's why we're concerned about moisture. It's a major aging factor. So begs the question, where does it come from? There's four main sources. Part of it is the residual moisture in the thick structural components, which the moisture that was not removed during factory dryout or due to moisture accumulation on the insulation surface during assembly in the factory or on site. And typically using that's a fact, because if the moisture is in those thick structural components, we're not that worried because the moisture is going to be locked up there. It's never going to move. Moisture from the atmosphere, breathing, open breathers during load cycles. And that's why you may have things like this silica gel arrangement to keep the air dry as much as possible from the oil, from the air in the conservator exposed to the ambient to try to keep the moisture out. But this is an item that needs to be regularly maintained and watched as to when to go about replacing that silica gel. And my favorite are leaks. through gaskets, through conservator airbags that have lost it, from weld pinholes. Um, understand what a leak is. When I look at transformers, when I walk in a substation, I look for leaks. And if I see leaks, I point it out, and I get told, well, yeah, that's just a little one. It's a seep, and they're not it's not hurting the environment because we're out in the middle of nowhere. I said, wait a minute. When you have a leak through a gasket or whatever, from the inside to the outside, oil may be seeping out. It doesn't have to be dripping out, just seeps. You've created a two-way highway that oil is coming out, but at the same moment, air from the ambient and moisture from the ambient is going in. It's a molecular highway now. So that is how moisture, one big reason why moisture gets inside the tank of a transformer is through leaks. So when you see leaks, big or small, seeps, whatever, please take time to fix it, do something with it, because you're only contributing to a reduction in life of the transformer because of accumulated moisture that stays inside the tank. And the decomposition of the paper and the oil during its natural aging process inside. When paper degrades in the transformer, it produces its own worst enemy. It's cellulose. And cellulose is basically a chain of glucose molecules all held together. And when they break because of moisture and heat, they break away, make a sugar, glucose. When it breaks apart, you have produced water. 3 parts water for every break in the cellulose chain. So, and there's billions, of course, in there. So that's where it produces water. It's a natural occurring phenomena that the only way you control it is to try to control the temperature inside and the moisture content. Now, it brings us to where is most of the moisture in the transformer? Well, when we look at the mass of insulation materials in the transformer, typically 90% of the mass is oil, 10% of the mass is solid insulation, cellulose. And it's composed predominantly 5% of the mass is the thick blocks that hold everything together inside mechanically. 2% are the barriers between windings and at around the ends of the windings, the collars. And 3% of the mass is the actual paper wrapped around the conductors of the transformer. But where's the water where's the water stored? The water distribution. As we all know, oil and water don't mix. The paper's there to suck it up like a big sponge. So the water distribution is 55% of the water in the transformer is in that thick blocks, and 22% is respectively between the winding paper and the thin press board materials. That's where it all sits. Now, in the transformer, the moisture is constantly moving back and forth between the oil and paper, and it's a function of temperature, which is a function of loading and ambient conditions. So if the loading is constant, the temperature is going down, transformer is running cooler, the oil is cooler, it wants to get rid of the moisture, and the paper is there to soak it back up like a big sponge. When it's hot and you're not overloading, but even bringing the transformer up to full load on a hot day, you are pushing now the water from the paper into the oil. And because the oil is hotter, it will hold now more water. So it's this back and forth. So there's a constant movement, and it's slow, constant movement of moisture between the paper and the oil over time, and it's all a function of temperature. So this effect is where you need to understand how wet is the paper, because it affects the aging rate of this winding insulation. It definitely influence the bubbling temperature. We'll touch on that. And also the dielectric resistance of the barriers at the bottom of the winding. This is from IEEE loading guide and the effect of temperature on paper aging. What we see here is aging acceleration factor. So you see the number 1 there, and you see 3 dots. So IEEE 65 is the standard that transformers are built mostly to in North America. 65C is the average winding rise, maximum average winding rise at a winding's hotspot temperature of 110 degrees C. If you can hold the transformer at the winding temperature of 110 degrees C for 24 hours, constantly, no change, It has an aging acceleration factor of 1, meaning it has aged 24 hours within that 24-hour period. Aging acceleration factor of 1. You can see that this is a log scale. So for every 7 degrees C above that 110 degrees C, the aging acceleration factor doubles. That goes from 1 to 2, just by an increase of 7 degrees C in winding hotspot temperature. Likewise, 7 degrees C less than 110, the aging rate is halved and continues to be halved as the winding temperature goes down. So that's the impact of paper temperature on the paper. The impact of water content on the paper is we apply it as 0.5% moisture. And what we mean by that is that that's the moisture content in the paper, the solid insulation, in terms of mass of water divided by the total mass of paper or cellulose inside the tank, 0.5%. And that is typically the go, no-go figure that's used to allow a transformer to leave a factory. It has to be dried to that extent. The moisture acceleration factor for that 0.5% is 1. You double that to, you put it up to 2% moisture content in the paper, the acceleration factor goes to 4. And it goes to 4% water content, you're up to now 8 or 7 times faster aging than if it was at 0.5%. This is, well, a logarithmic function. So when you put the two together, temperature and moisture, you can impact, as you can see now, that the two have an impact that accumulates or speeds up the aging factor of the transformer, aging rate of the transformer, aging rate of the solid insulation. That's why we have to have a very good idea of the water content in the paper. Another graph from a C-grade publication number 322 showing the life expectancy. And again, we're looking at temperature, winding temperature across the bottom, and life expectancy in terms of years. It's a log scale. And dry paper, you can see if you can keep paper dry to 0.5% over a long period of time, which is like impossible. But this is all theory at the moment. It can last a long time. But if it goes to 1%, it's going to be living half the life at 70 degrees C or 110 degrees C versus dry. So this gives another indication of the life of the transformer, active part in terms of the effective water content on the craft insulation. So how do we do this? How do we determine how wet's the paper? Fortunately, thanks to people like T.V. Uman, who was a researcher with Westinghouse and then ABB in the United States, did a lot of research here. So we're looking at equilibrium curves to convert moisture dissolved in the oil, percent saturation, into moisture in the paper. But we need to know the temperature of the oil-paper interface and the thickness of the paper. And you have to integrate these values over a long period of time. So if we're looking here at the bottom of 20% saturation, which I said before was kind of like the limit of where we want to be in the oil. So this is a measurement of relative humidity in the oil. You run it up to 20% humidity. I don't know where that little dewy thing is. Oh, here we are. 20, run it up to 20 degrees C, and run it across here. You're about 3.5% wet. If humidity of the oil is 60%, and the winding hotspot temperature, that's what we're looking at here, is 100 degrees C, you're really wet by this point. You're at 4.5. Anywhere between 3 and 4, 3.5%. My feeling is between 2.5% and 3%, 3.5% is the maximum you want to be at to avoid things like bubbling and also reduce the risk of reduce the aging rate. That's the chart. Time is the other function. This is the diffusion. So there's a diffusion time constant between the oil and the paper. For 1 millimeter paper wrapped down the conductors, if you could have it at 80 degrees C for some period of time, you will reach this equilibrium point where the moisture has stopped moving between the oil and the paper. 80 degrees C, 1 millimeter paper. It's like just less than a day. If the temperature is 60 degrees C, 1 millimeter paper, it takes 4.2 days. If it's 20 degrees C, it takes 93 days. That's how slow this is. And it's all a function of temperature. And that's when we talk about online monitoring, which Chris was on the breaker side. From the transformer side, we take this into account to calculate the total aging rate. So over time, people have done this work of taking ppm and translating it into moisture and paper. Fabre-Pichon from the 1960s was the first attempt. TV Human tried to update that in 1993, ppm and moisture and paper. The thing is, we don't know the saturation curve. We'd have to know the saturation curve. And the transformer must be a more or less thermal stability condition, which unfortunately never really happens. So we now know we need temperature of the oil paper interface, and that implies the winding hotspot temperature. The diffusion time constant, we have the table. And the facility of integrating results over a long period of time, which is possible now with online monitoring transformers. So now, to complicate our dilemma, moisture content in the solid insulation is not a single value. There is a correlation between the amount of water in the oil and the paper, and this correlation is dynamic, as I was saying. Dynamic means it keeps moving back and forth as a function of temperature and induced by loading or by the ambient. We ignore totally the thick insulation around the core and the winding blocks. And the interest is the lowest part at the winding of the barriers at the bottom of the winding, and the dynamics of distribution of the water is quite complex and changing. So what this looks like, TV Human, then part of his research he built this set of coils, dried them as you would in the factory, inserted them into a glass tank, filled it with oil, and the two of them in separate tanks, and then began to carry out experiments. So he began to doctor or make the oil wetter and wetter, and therefore make the paper wetter and wetter. And this is where he was able to demonstrate using this that he could induce the moisture coming out of the paper in the form of steam, water vapor bubbles. That's steam. It's on top, and you can see water vapor bubbles underneath. And off this one here, now this, you can see the water vapor bubbles streaming up somewhere into the upper part of the transformer. And these are, again, water vapor bubbles. This is not combustible gas bubbles. Don't get confused on that. This is steam. And this is how they came up with this. So Uman's curve, when bubbling is predicted, is a function of temperature, the hotspot temperature, and the water content in paper when the point in time has come when the moisture has stopped moving. So if we're at 0.5%, we're way down here when a transformer is new, this curve says they should be able to load it up to 190 degrees C hotspot temporarily before bubbles form. But in normal operation, we would never expect to go above 110, overloading maybe to 130. But at 2% moisture content in the paper, bubbling is predicted to occur at a winding hotspot temperature of 140. If it's 4% wet, bubbling is predicted to occur at 110 degrees C hotspot, which a transformer by standard says you should be able to run forever, but only if the paper is dry to 0.5% water content in it. And that's the point of this understanding, why we want to know how wet is the paper, and all this research done by these gentlemen. So when you cut the transformer, when you slice it in half, as I say, and you look at it, you have convection. This is a cross-sectional view. In the transformer, you have a temperature gradient between bottom and top of the tank, right? It's cool. The oil is cooler at the bottom than the top. There is a winding temperature indicator gradient, and it's cooler at the bottom than the top. That's just the way it works. It's physics. Moisture content in the winding is a mirror image of the temperature. So it's drier at the top because it keeps pushing the moisture out more than the bottom. It's cooler. So the moisture isn't coming out of the paper as much. And then you have the thin barriers. This is between the phases, between high and low voltage, so to speak, where you can have quite a difference. And this is so the area of interest from a online monitoring perspective is understanding how wet it is at the barrier insulation. That's where partial discharge can set itself up. And the area of interest at the hottest spot on the winding at the top, and understanding this from the bubble temperature evolution and from the aging point of view as well. Those are the two areas of interest, and we can get that with online monitoring. And you can see there's can be a significant difference in moisture content in the paper, 1.2% in the paper at the top because it's hotter, and 3.3% because this is thicker material and it's cooler. So it's a difference. So how do we handle all this stuff? We kept saying it's about equilibrium. Well, a few years ago, this transformer was donated to the University of Stuttgart in Germany by a utility, and there's some details on the transformer itself. They let this transformer sit in the lab, as you see it here. This was a forced oil transformer, and they just let it sit there for 18 months with just the oil pumps running. No load, no voltage, no current. They wanted to achieve the state of equilibrium, and where the oil in the water and the oil in the water and the paper were in equilibrium. In other words, it was not moving back and forth anymore. Once they achieved that, then they began to apply different measuring techniques. The dielectric things like frequency, FDS, the Duranda product, they were measuring differently between 3 and 4% total water content in that block of solid insulation. The equilibrium based on Carl Fisher test of oil was vastly overstated. That's why we don't use ppm water and oil. Forget about it. Use the oil saturation values, the measured oil saturation. And here it was around 2.5%. And then the proof in the pudding, so to speak, was once it was all said and done, they went in and they took paper samples out of the transformer and dried them in the lab. So you can take paper samples from the transformer and weigh them in the lab, and then put them into an oven, bake off the water from the paper, bring the paper out and weigh it again. The difference in mass is how much water was in the paper. And that's how they determined this. So when you look at the equations that we talked about from Uman and the others, and the measurement of moisture saturation, it's as close as spitting to what was actually measured in the paper sample from lab work. So this report can be found on the Seagrave website. It's the Southern African Region Conference in 2009. This opened up a lot of eyes. I was there when they presented it, and it's people have followed this, and it's the proof in the pudding, so to speak. So it shows that paper at different temperatures have different moisture levels. As temperature changes, so does the movement of water inside the transformer between the oil and the paper. In practice, perfect equilibrium never exists, but by dynamically monitoring it over time, you can derive that point in the magic point in time when equilibrium is occurred. Now, from this, we can determine the bubble evolution, an alarm point, and I'll come to that here. Here we have, this is a transformer connected to a solar farm out in the outback of Australia. And what we're seeing here, this is the moisture and oil sensor and hydrogen sensor. The monitoring system is attached on the other side of the transformer. We're monitoring everything on this transformer. What we see here in blue is the measurement of relative saturation of moisture in the oil. And the scale here is around 4% to something over 7% saturation. But you can see it's cyclic, it's going up and down. The gray is the primary winding hotspot temperature calculated by measuring oil temperature and load using the equation. It's close to 100 degrees C. It's hot. And in orange is the moisture top oil temperature of the transformer. So what we compute then is the point at which we've taken into account the equilibrium time, and we look at the margin between the maximum winding hotspot temperature and the temperature at which bubbling is predicted to occur. That's the margin. The margin is the alarm point. When this value becomes, as the paper gets wetter, this value is going to come down. When it reaches 20 degrees C, the margin, the alarm goes and say, hey, stop, reduce load, do what you have to do. But if you don't reduce load, you're going to reach a point of no return in terms of bubbling and shorting out the transformer. Now back to that case I showed at the beginning, that GSU, that single phase, in the forensic analysis. Moisture in the paper caused this dielectric failure, in this case in one of the most highly stressed area of the core and coil assembly. So you can see this high voltage lead coming in, and this is on extra high voltage transformers. This is a common way to bring the power in. You have two high voltage sections. And by again going in and taking out paper samples, we managed to find this point where it failed. It was through the barrier, high voltage to low voltage winding is where it happened. They had used the conventional oil processing and means of drying the paper transformer, but it was ineffective because you just dried the oil. You didn't dry the paper. And the moisture content in paper, as determined by doing all the samples in the lab, was at 3% in this area. And you had this impact. So the oil processing as a means of drying the paper insulation was ineffective in this time frame. And looking over the previous data, there was no online monitoring on this transformer. Looking over the data over time, looking at this, a bit confusing for some people. They really didn't understand what they were looking for. There were no alarms from this indicating, like from a monitoring system, indicating the moisture was coming out of the paper and back into the oil. And it's an estimate, whatever you're using, it's an estimate and it's an average. But the important thing is they didn't dry the paper. They assumed that once the oil was dry, we're good. And that was not the correct decision to make. And acceptable limits of moisture content in the oil and paper were unclear to them. So how do we do it in the field? Well, the physics of drying involved three things: the moisture gradient, as I was showing before, top to bottom, a temperature gradient that determines the thermal diffusion time constant, and the pressure gradient. This is the convection diffusion time constant. So these time constants are different. They're long. So the best, fastest, and most complete solution involves all three of these into one. And conventionally, what we've been doing for years, some people call it rip and dump. You apply heat to the oil in the transformer. You circulate it through the oil processing unit. You circulate it. You try to bring up so you're inducing heat from the outside through the oil and trying to heat up the windings and the solid insulation by inducing hotter oil, not real hot oil. And then suck the oil out. And as you're circulating it, trying to suck the moisture out of the oil. And at some point you apply vacuum to the whole assembly with the oil out of the tank, or most of the oil out of the tank. Now that implies the tank must be fully vacuum resistant. You have to make certain of that before you start this. Now the thing is here, when you apply vacuum to anything, what happens? You lose all the heat. In a vacuum, there's nothing to hold the heat. So what happens inside is that things get cold quickly and things turn to frost. Once the vacuum is over, then you have to go back and heat it all up over again with hotter oil. This takes a long time. With low frequency heating, which is this technique has been around for at least 12 or 15 years. It's been commonly used in Europe and in some places here in North America. It's basically a combination of heat and vacuum. And again, the transformer has to be able to sustain vacuum. And the difference here is that there's a power supply that will energize. We apply to the transformer, and you'll short out the primary side, apply current to the low voltage side, and at a frequency of 1 hertz, not 60, 1 hertz. That way, from a dielectric perspective, you're not going to hurt anything inside the transformer, but you will certainly be heating up all of the windings. So you can apply 300 or 400 amps. And that's a function of the design of the transformer. That's figured out beforehand. So the windings are always heated. So it's always pushing the moisture out of the paper and into the oil. And then time comes to evacuate all the oil, and then a vacuum is applied. But it doesn't get cold again. Heat is still going, current is still flowing to the windings. So you're still pushing the moisture into the vacuum from the windings under a vacuum, because you don't remove the power supply. You don't remove that 1 hertz supply. So you're heating all the windings uniformly. It's a much faster, more energy efficient way of doing it. And you minimize any aging due to damage to the insulation system by virtue of a controlled temperature and a better control of the drying process. That's low frequency heating. And this comes from a paper that was written, Seagray paper, where somebody had gone away and decided what's the drying time to drive a 400 MVA transformer with 14 tons of solid insulation inside the tank to lower it from 3% down to 1.5% average humidity. So the conventional way, online oil degassing, an average temperature of 50 degrees C, the process I just described before, it's like 115 days. The other one was hot oil circulation and vacuum cycles, 76 days. And somebody has to be there watching this and babysitting it. Low frequency heating and hot oil spray, 9 days. Vapor phase, you see on the far right-hand side, far less. That's the process that's used in a transformer factory. Vapor phase drying of the Correns coil assembly in the factory. But heaven forbid, you're not going to send this back to the factory to be dried. So low frequency heating does 2 things. It is dried out more efficiently to a better result in much shorter period of time. And time is money to a utility and the operation of a transformer. So that's where we are, Randy, with moisture and low frequency heating of drying a transformer.
And excellent presentation, Brian, as always.
Thank you, Randy.
Lots of questions. Are you ready?
Yeah.
Okay. Now you have to forgive me. I don't know the acronyms for these. You'll probably guess them.
All right.
Is WCO RS affected by the slight pressure vacuum inside the case?
WCORS, relative saturation, the pressure inside the case.
Yes.
No. The simple answer is no.
Okay. Next question. Will pressurization with nitrogen help to protect oil transformers against moisture accumulation?
No.
Geez, Brian, it is really easy.
I mean, no. I'll explain. If you maintain the nitrogen pressure, it helps. It's there to help keep it sealed, to keep the transformer sealed, right? To prevent. Now, if there's a leak on the transformer and nitrogen sealed, right? You have the oil seeping out. You're still going to have air coming in because it's a molecular highway, right? Mm-hmm. I've seen cases of, and this is a wild ass case of a transformer. It was going through 1 bottle of big 40-pounder of nitrogen bottle a week. Mm-hmm. And looking at the DGA and all this sort of stuff, and it made me wonder what's going on. And there was a handwritten note on the report. Mm-hmm. It said, you will remember that this transformer has a leaking high voltage bushing on the cover. So the nitrogen that they had to pressurize to try to keep moisture out during the process, they were going through 40 pounds of it in a week, was also driving off all of the dissolved gases. So it's scavenging all the dissolved gases away from it. Moisture was still getting in because it's a 2-way highway. And so it's there. If things are sealed up, it works. If it's not sealed, no, it's still open to the atmosphere.
Okay, good. Next question. Do you also consider the principle of void within the paper and transformer winding conductors?
The void in the paper. Well, the paper itself is going to have voids in it. That's just the physical construction of the paper. Paper that we write on from a chemical. You've got my electron microscope out and looked at paper that we're writing on, Randy. You're going to see voids, right?
Yeah.
You're going to see fibers. You're going to see all that wonderful stuff.
I think I asked you this question before.
All right.
So I'll ask it again.
All right.
Why do we still use paper? Is there no better material than paper after all these years in transformer design?
There is. Yes.
Okay.
It's called Nomex.
Okay.
And it's impervious. It doesn't absorb water very well, right?
Mm-hmm.
And the big difference, Randy, is money. So, and I've had asset managers ask me the same question, right? Haven't you guys figured this out after 100 years, right? What's wrong with you? I said, we can do it. And I've done it when I was with Maloney. We used to build some units with Nomex. Are you prepared to pay 20% more for their transformer to have it live forever? No, carry on. That was so. It's all related to economics, Randy, and application. Let me say
Right.
that.
I understand.
Yep.
Okay. Yep. And I know that answer because I've asked you that question many times.
I know.
But for the benefit of the group, maybe
yes.
some people don't know that. It's
Why
all transformers are all about asset management is all about money, right? It's economics.
That's right. It's risk and consequences, right? That's what it's all about. Yep.
Right.
Yep.
Next question. Is it known that the behavior in relation to humidity is different? It is known that the behavior in relation to humidity is different in mineral oil and in vegetable oil.
Yes.
How much difference exists from the point of view of transformer maintenance?
Oh, good question. I'm assuming that they're talking about maintenance of the fluid itself.
Yes.
That's my first inclination. I don't know the answer. I do know that within IEEE committee, working transformers committee, which is meeting in a week's time, week after next, here in Vancouver, that there's a new guide coming out. It's going to be called C57.166, which is going to be called a maintenance guide for insulating fluids for transformers. And it's going to cover all 4 basic fluids. It's oil, it's natural esters, synthetic esters, and silicone. Now, I have not spent any time studying it at this point in time, but that guide was being balloted now, and hopefully we'll find out when at the meeting in 2 weeks that when it's going to be published. But there are different methods for maintenance of the fluids. That's not just true. The thing is, natural esters will hold more water. Paper is still going to produce water, and it's going to go into the fluid. It's going to stay there. But I have not studied the dynamics, let me say, of when for instance, when water's going to condense in that fluid and rain. I don't know. I just don't know. That's the next study. That's the next study project. Yeah.
Yeah, maybe we can convince you to teach a course on that.
That's right. Yeah. Yeah. All right.
Sounds like a good idea.
Yeah. I think so. I think it's that sort of sharing knowledge. You have all these fluids and
absolutely.
Yeah.
Good. Next question. Are online insulation moisture monitoring equipment in transformers immersed in vegetable oil and mineral oil at the same time? Or how many differences are there between them?
In terms of the sensors used, there is no difference. You're still measuring moisture in a fluid.
Right.
And the unit of measure is still 0 to 100% saturation.
Okay.
Now, you need to calibrate them. You have to tell the people that make the sensor, oh, it's going to be used on synthetic ester or oil. That's fine. But they need to know that so they can set the calibration correctly. But in terms of physical, it's still 0 to 100% saturation.
Right. How frequently, next question, how frequently should this online monitoring data be reviewed?
Online monitoring, and I'm going to speak in generalities here.
Yeah.
Online data, and that question comes up a lot. How often do I have to look at my monitoring data? And I've been around doing this, Randy, as you know, a long time. And I've come to the point in saying, only when the monitor tells you there's something wrong. And that's honestly, you can drive yourself crazy looking at squiggles on the graphs and all that sort of thing. Right. The time that you want to know what's going on is when an alarm comes along and it says, hey, I got a problem. That's when you want to go to it and look over the data leading up to that alarm, like the week or the month before. That's the time to look at the data. Otherwise, if nothing's happening, it's like no news is good news, right? Randy, that's the old adage, right?
No news is good news.
Yeah.
Okay, next question. Are you providing the the presentation? Yes, we'll be. I've already dropped Brian's presentation into the chat. I'll do it again.
Okay.
And after I finish the questions.
Very good.
Many utilities, next question, many utilities keep an oil-filled spare, but not maintained, tested, or have the oil circulated. Will the craft degrade over time? What should be looked for when sitting spare is to be brought into service?
Number one, you should be doing regular oil sampling on that spare all the time it's sitting there. So if it's critical, I would do it once every 6 months. Pretend it's in service. Go there and do a DGA. Go there, take the samples for color, acidity, interfacial tension, all of those standard tests. Build up the record. And if you see something happening while it's there, because leaks can happen if it's sitting there. Think of an old car, Randy, right? Mm-hmm. You have an old car with that gasket starts to leak.
Yeah.
Same is true with a transformer. It can happen. I've seen old spares sitting there, and I think our buddy Chris on there was saying about kids, throwing stones at bushings and whatnot before. Kids, you get into the darndest thing is throwing. Let's see what happens when I do this, right? And the spares are normally sitting in the back 40 of a yard somewhere. So you never know what the hell's going on. And it's best to keep testing those things. And before you take it out and put it in service, make sure you do a really good test for moisture on there.
Yeah. Okay, last question. How prevalent is the use of LFH in the US for transformer oil installation maintenance?
It has been in use in the States and in Canada, Randy, for the last 10 years. That's from the number of papers that have been published on the topic. That's the experience that I have seen, and people are not afraid to show, here's what I've done and here's the results, and it works. And the system that we have coming to us, that we have it in Toronto, and by April, the machine itself, we'll have it, and I think we're going to plan an open house, Randy, or something like that. So great. Whenever it is, we'll give you an invite down. Come on down and have a look.
I'll be there.
All right.
But for my benefit, what is LFH?
Low frequency heating.
Great. Okay. Yep. Okay. That's great.
And it has been described in standards. I was part of C57 170, which we call the Life Extension Guide of Transformers. I was the vice chair. This method is described in that standard, and that's now pushing 10 years old. It's up for renewal.
Right.
And it's also in the Seagrave Maintenance Guide of Transformers, and that was published in 2011. Mm-hmm. So this, like I said, this technique is not new. It's been around a while. Processes have been improved over time. Microprocessor controls now, instead of somebody standing there with an old analog gauge doing things, Andy, it's we have moved forward from that point of view.